Hi, everyone. In this video, I'm going to talk about dynamic programming, which is a common technique in designing algorithms. Dynamic programming is an efficient tabular method for solving divide and conquer problems. By tabular methods, it means that we're going to create a table and then fill in intermediate results. And this process of making a table is called programming before computer programming was invented. Okay, so suppose that we have formulated a recurrence relation for solving a problem of size n. And we call this a problem P of n. So P stands for a problem, and n is the parameter size, and which then relies on a number of subproblems. Let's call them P of K1, P of K2, up to P of Kn, where Ki is less than n. And m here may be a constant or a polynomial of n. Polynomial of n means that in the order of n to some power, constant power. We further assume that there are only polynomially many different subproblems. Okay, so which means that if you look at, this is my problem P, and the input size is n to begin with, and then in order to solve P of n, we're going to break the parameters into sub parameters. So this is K1, K2, up to K sub m, and we are going to solve P on these smaller size of inputs. And by combining these solutions to these subproblems, then we can solve P of n. Likewise, in order to solve the subproblem with size K1, we may need to further solve subproblems. Further solve subproblems with smaller size of inputs until at the end, the boundary, when you reach the boundary that the problem size becomes 1 or becomes some constant that you can solve them right away, then you stop. Okay, so this is the boundary. Okay, so that is the problem we have. Okay, so this is not that hard if you are allowed to use direct recursion, because we already figured out this recurrence relation. But the problem here is that we may end up repeating the computation of the same problems many, many times. Okay, so which means that, for instance, there is a subproblem P of K, and then so let me put it here. So it's a P of K. So this is a particular subproblem, and then in order to compute some other things, let's call it M, it will need to compute P of K. Maybe the other one also n prime, it also may need to compute P of K. Maybe there's some others. So which means that for each of these subproblems, then you will end up computing the same subproblem. So if you use direct recursion, then each recursion will have to recompute this same problem. So using tabular method means that we're only computing this subproblem once, and then we record the value there. So when next time you want to get the result of computing this subproblem, you don't need to repeat the computation. Instead, you will just need to do a table lookup. Okay, so that is the idea of dynamic programming. And then we are going to look at in detail how this is done. Okay, so once again, so we would want to store solutions to the subproblems once they are computed, so that when the recursion comes to call for a solution to a previously computed subproblem, we only need to do a table lookup without repeating the same computation. Recomputing a subproblem may be costly because you may have a lot of function calls or the recursion calls of that subproblem. Okay, so which may end up actually exponentially many computation of the same problem. So in general, there are approaches to carrying out dynamic programming. One is top-down recursion, and then we need to memorize the intermediate results to memorize the results of computing the same subproblems, right? So we create a table to store the results to subproblems, or bottom-up tabulating without recursion at all. So we can completely remove recursion. And this approach cuts down the computation overhead for handling recursion calls, but coding is slightly more involved than top-down recursion. So top-down recursion is pretty straightforward in terms of coding. So first, let me use several examples to explain this technique. In the meantime, I also explain why direct recursion will end up exponential the many steps in order to compute P of n. The first example is computing Fibonacci numbers. So Fibonacci numbers is the following series. We begin with 1. Okay. And then, so let's say the index is from 0. So this is the index. And for the first two numbers, so we begin 1 and 1. So we begin with 1 and 1. And then for the next one, it will be the summation of the previous 2. So this will be 2. This will be 3. And for 4, this will be 5. And 5 here will be 8. Right? So you can just going in this direction as far as you want to go. So in general, the definition is the following recurrence relation. Fib of n is equal to 1 when n is equal to 0 or n is equal to 1. And when n is greater than 1, then it will be the summation of the previous 2 numbers. So which is a fib of n minus 1 plus fib of n minus 2. Okay, easy enough. Then we can use a direct recursion to compute this, right? So it's straightforward. when n, if n is equal to 0, n is equal to 1, return 1, else return fib of n minus 1 plus fib of n minus 2, and the function here is a fib of n. And then let's say for n in the range of 40, where we want to compute all of the Fibonacci numbers up to fib of, in this case, a fib of 39. Okay, so let's run this. Okay, we run this. Now, as you can see, it still runs. It's still running because you see that if we do an analysis, then we'll see that certain subproblems will end up being computed over and over again. So this is fib 39, and then it's the previous two. So this is a fib of 37, and this is a fib of 38. Okay, and then for fib of 37, this will be, I use F, right? So this is Fibonacci, indicates the Fibonacci. Now it's still running. Okay, now it's done. Now it's done here. So it takes a while. And so this will be 36. Let's say we do 35 first, and then 36. And for 38, you will need to compute, see, it will rely on 37. Compute 37 and then 36. All right. So which means that for 38, you will need to recompute. Now for 39, you compute it once. For 38, you compute it another time. And for the F36, it will be used in 37, and then it will also be used in 38. So then this has to be computed twice. Okay, and then 35 will be 34, 33 first, and then 34. And 36 will rely on 35 again, and then it will rely on 34, right? So as you can see here, so these will be, for instance, in order to compute 37, so 37 will be used in for 39 and 38, but 37 will have other subproblems. So these subproblem will be 35 and 36, and 35 will be used again, right, by 36. So that it's repeated. Okay, so let's do one more step. So this will be 32, 33, and this, and then it also depends on, so this is 33, right? So this is 31, 32. So 33 will depend on 33 and 32. So obviously you will say, okay, once I computed 37, then I should store it. But then this is a recursive call, so you have to go down to the bottom and then remember the one that on the bottom. So this is the boundary. All right, so now in this example, first we run the code and we see that even for n small, which is 39, it took a while to finish the computation, and then I'll explain why subproblems are repeated over and over again. So now use tabular method. First let's just look at why it ends up at exponentially many steps to compute fifth of n. According to the recurrence relation, so we let T of n denote the time to compute fifth of n. And so for the boundary, when n is equal to 0 or n is equal to 1, so it's 1. Otherwise, it will be the time that T of n minus 1 plus T of n minus 2, and plus 1 because we have to do the addition. So this is just the time. We have to compute both of them. So both of them, so this is for time. And this one comes from the actual addition. So this is so this comes from computing this time, computing that time. So the time will be the time of two subproblems. So you have to add them up. And this, again, this is one we just think about. You add two results, and that takes constant time. So we are using one to represent it. Okay, so now we want to get the lower bound. So the lower bound, and we can, obviously, we know that T of n minus 1 will, so T of n minus 1, obviously, will be using more than T of n minus 2. So then we can just say that there are two copies of T of n minus 2, and this is greater than or equal to. And so then once we have this, so which means now I have T of n greater than or equal to two copies, and that in the early example, I already showed you. So for each of those, it will have to rely on two copies, and then this will be greater than or equal to 2 times T of n minus 2. So once I have this, we can iterate this. Okay, so we can iterate it. So for instance, for the next iteration, we get 2 squared times T of n minus 2 squared plus so for this, so yeah, let me write one more step here. So this will be 2 T of n minus 2 squared plus 1 plus 1. So this is going to be 2 squared T of n minus 2 squared plus 2 plus 1. So you do one more step, you get 2 squared 2 times T of n minus, and this time you got 2 times, each time you got, you have this 2, so maybe it's better to write it as 2 times 2. So this will be 2 times, so there's a 2, actually I should say it this way rather than making it making it as a multiplication. Is actually, so let me rewrite this in a better way so that so to make it easier to generalize. So this is 2 times n minus 2 minus 2. okay, plus 1, plus 1. So this is going to be n minus 2 times 2 plus 2 plus 1. And then this is going to be n minus 2 times 2 minus 2 again plus 2 and then plus 2 plus 1. So we simplify this. There will be 2 to the 3 times t of n minus 2 times 3. Okay, and then plus 2 to the 2 plus 2 plus 1. So now it looks like this is going to be the number of iterations. So for the case iteration, we are going to have this. So greater than or equal to, so which is going to be eventually, right? So case iterations will be 2 to the k times t of n minus 2 times k, and then plus, so this 2 is 1 less than 3, so it's 2 to the k minus 1 plus, and down to 2 plus 1. Okay, so that's what this is for. And when do we stop? So when n minus 2k is equal to 0 or is equal to 1, then it stops because that is the boundary, so which we have 1, which means that either n is equal to n over 2 or k is equal to n minus 1 over 2, depending on what n is even or odd. And then that's where we stop. And hence we have t of n. Now, let's figure out this one, right? So it's 2 to the k minus 1 plus 2 to the k minus 2 plus 2 plus 1. So this is just 2 to the 1, this 2 to the 0. So we know that using geometric summations, we know this is going to be 2 to the k minus 1 minus 1. Okay, so that's what is this. So that we have then, so we got 2 to the k. So when k is equal to n over 2 or k is equal to n minus 1 over 2, then we stop. So which means that we get t of n is equal to 2 to the k plus 2 to the k minus 1 and minus 1. Okay, so then we can just say that this is k here is either n over 2 or k here is equal to n minus 1 over 2. So what you're getting is this. So now, oh, I'm sorry, this is, so when you add them up, it's 2 to the k minus 1. Okay, so it's 2 to the k minus 1. So this then is equal to 2 to the k times 2. So it's 2 to the k plus 1 minus 2. All right, so as you can see here, this will be greater than or equal to 2 to the n over 2. So this is exponential. Okay. Yeah. And from the previous drawing, we know that the height of that tree is n, and each time we have to repeat the computation of the same problem twice. So roughly, right? So roughly, then it should be exponential. But then this is lower bound, so we get down to the lower bound, and hence we know that direct recursion is not efficient. All right. So now we know we want to record the results to subproblems. And then how do we record them? Well, in this case, we can just use an extra list to remember it. So we're going to use memo to represent memorization. So when you get down to the bottom, okay, so this is 0, and this is going to be Fn, right? So this is 1. Now let's call it n here. So then, so what you end up with is that when I compute a particular input, this time I'm using FIB and FIB, and with an extra table. It's a table. In this case, it's a linear table. And we will first check to see whether I have already computed that problem. Say this is, if I use, this is n is somewhere, right? So if I have already computed that subproblem, that means that I have a value here. So I will first check it to see if memo of n is not 0. If it's not 0, that means I already seen that subproblem. In that case, I will simply return that value rather than recomputing it. Okay, otherwise, okay, so at the beginning, they are all 0, right? At the beginning, they are all zeros, and then we're going to check to see whether n is less than or equal to 1. If it is, and then the value should be 1, right? So we compute v is 1, and then we're going to assign v to memo of n and return v. Otherwise, we're going to compute this subproblem, and then I will store the value to v, and then assign that v to memo of n. So essentially, it just end up like this, right? Essentially, let's say I compute this, and then I'm going to look at its previous 2, and they are 0 because to begin with, and then we have to look at its previous 2. For this, look at its previous 2. It's end up 0 until I end up here. Oh, look at its previous 2. Oh, haha, that I have value, then I'm going to, so this recursive call, then I can get down to the bottom, and then I get the value, and then I'm going to, so it becomes 1, right? So this boundary condition, this becomes 2, and then it just, you work your way up, and then you solve this problem. All right, so now let's see. We're going to run this, right? So this time, now remember earlier, when I said n is 40, it took a while to finish that computation. Let me just say I use 40 here. You see, this is instant. Okay, I'm gonna compile this and then run it. See, it's done just in the blink of a second. And you put 2, much bigger. It's also done in a blink of a second. You see, this is a huge number. Right? So this is this big. All right. Okay, so because Why it is the case? Because it's a linear time. Why is a linear time? We just need to figure out each subproblem is computed once, okay? And then how many subproblems do we have? So we have linear many, right? So for n, then we have n minus 1 up to n n is equal to 0. So there are linearly many subproblems, and each subproblem is computed once in this case, and then hence the computing time is just linear. All right, so that is that explains why this is so fast, so efficient, so fast and efficient. Okay, the second approach is to get rid of the recursion completely. And we can just look at, so in this particular case, as we analyze our case earlier, when you do recursion core, you will go top to the bottom, top down approach, from the top to the bottom, and then you work your way from the bottom up. And so in this case, I will just start working on my way from the bottom up, and that you don't need recursion. So in other words, what I'm going to do is to start from here rather than you start from in the middle of it. So I'm going to directly start from here and place them. So this is to begin with, we have 2 1s, and then we can just compute. So this n goes to this direction, and then each time I'm going to sum up the previous 2. And so on, right? So this is a bottom up, and bottom up is more efficient. And then in this case, it's also very easy to write. So in this case, we will just say, okay, this is going to be my memo. Okay, and then, so I start with 1 and 1, and then I'm going to just, so I starts from 2 up to n minus 1, and then I'm just adding the previous 2, and these, they already have values, and hence this is also linear time. So it's going to be quick too, very fast. So n is 240, right? So also blink of a second, and we're done. Okay, so this is a simple example explaining dynamic programming, the idea of dynamic programming, and also explains why we would need to use dynamic programming. And so this is, if you think of so this is divide and conquer in the case that subproblems may end up being looked at many times. And this is different from divide and conquer sorting algorithm, because in that case, in sorting, subproblems, they don't need to be recomputed. The same subproblem, they don't need to be recomputed. But here, whenever subproblems would need to be recomputed, then we can use the memoization technique by recording the results to subproblems in a table. Hence, it is called a tabular method, and hence it is called programming, because that was what people understand as programming before computer programming was invented. Okay, so this is the end of this video. Thank you for watching.